Okay, so today we're going to finish off sort of part two of this conservation of mechanical energy and the work energy principle. What that's going to entail is considering friction a little bit more than we did last time. So in the part one to this, we made use of these conservations of energy, but I didn't incorporate friction into the questions I asked you to do at the end intentionally, so you could practice these kinds of questions without including friction. I'm going to change that in this part too. So although in the previous part you did an example which included friction, now I'm going to have more questions at the end which are going to include friction in it as well. So what I'm going to do is, after this initial question, I'll just have one more example that I want to run through, and another point I want to make about finding a distinction between work done by a force and against a force, and then after that it'll just be some questions for you to try. But before we get into that, there's a thought here in this question that I'm asking on screen, and it's something that may not come up that much in a lot of these questions, but it's definitely worth thinking about, because at a more advanced level, this is in fact the case that the driving force on an object is not going to be constant, right? So in fact acceleration is not even constant, and we saw an example of that in previous questions, but what I thought we'd do is consider this simple case, right? This relatively simple case. A box is being pushed along the floor by this driving force D. So you can just sort of imagine it, the standard sort of thing, horizontal floor, no friction in this case, and there's some force D, but it's not a constant force, so it's changing. In fact, it's increasing. It's initially 5 newtons, and then it increases steadily at a constant rate, and we don't necessarily know what that rate is, but it is a constant rate such that after the box has moved 100 meters, D is now 10 newtons, right? So we've got effectively, in terms of before and after, let's just draw it out. Okay, so 5 newtons initially, 10 newtons as a final, and 100 meters separating these two different states. Okay, we don't know how long it's taken. In fact, we won't need to for this question. All that matters is that we have been definitely guaranteed that it's a continuous increase at a constant rate. And what we're now going to answer is the question, what is the total work done by the force D over this distance? So come up with a number if you think you can. It's technically the case that you would need some form of calculus to answer this. However, you don't actually need it to come up with an intuitive answer. So see what you think. 100 meters, a force that steadily increased from 5 to 10. What do you think the work done is? Pause the video and then I'll explain. Okay, so I'm going to remove the image, and the answer is, in this case, 750 joules. But I think it's easy to sort of trick yourself into thinking you understand why, but it's important that we don't make too many assumptions. So that is the answer. Perhaps if you got it, you were thinking something to do with averaging 5 and 10 to get 7.5, for instance. So if you average 5 and 10, get 7.5 times 100, you get 750. That works, but it kind of hides the reason why it works. So I think a clearer explanation of why that works is to draw a graph. And what we're going to do is we're going to plot the driving force, let's call it D, as we did before, against the distance. I'm just going to swap those. So the distance S against the driving force D, and S ranges from 0 to 100, and D is going to vary from 5 to 10. Now, I'm going to draw a graph of what does it look like if it was just 5, right? So if it was 5 newtons the whole time, then the graph of what happens would be this, right? It's 5 newtons at every single distance from 0 to 100. If it was 10 the whole time, then it would be this, right? And then notice that the work done, much like a sort of speed time graph, the area underneath has meaning, right? So in this case, the work done is the area under the graph, because distance times force in this case gives me the area, but it also gives me work done. So much like a speed time graph, the area underneath it is going to give you the distance or the displacement, or however it is. So this is the idea: is the area is the work done. So if we consider the area being the work done, then let's mark in red our actual graph. It's going to go from 5 newtons, and then it's a steady increase. And because it's a steady increase, we can mark it as a straight line. Okay. This area here is 500. This area here is half of 500, is 250. So the area is a total of 750. And that's it. The answer is 750. At a higher level of mechanics, it may unfortunately not happen within this textbook, but at higher levels of mechanics, you can see how you could start to use integration to find the area under a curve of a driving force which varies not steadily. So maybe you have a function which describes the driving force, and then you could integrate that function with respect to distance and get the work done. So this is just a teaser to that, I suppose. We're not going to be using this necessarily in this lesson, but I thought it was nice to mention and to just clarify in your minds this idea that even if a force is variable, it's still quite easy to define the work done. And this is one such way of doing it, as an area under a graph. Okay, so then before I look at one more example in this topic, I wanted to clarify the difference between these two terms, just because they come up a bit. And really, they're talking about the same thing, but it's just how you interpret the situation. So it's more of an English language problem, I suppose, than it is anything else. There's not like some big technical definition which varies between the two. So the idea is this. Let's go again with objects on the floor. Okay, and let's say this green line tells me the direction it's moving. Okay. Let's say I apply the following force to the object, okay, and it's some driving force, D. It's at some angle, and it's not horizontal in this case, right? So the question is this force an example of work being done by the force, or work being done against the force in some sense? So all it ultimately amounts to is considering the components of the forces, and one of the components will always be vertical to the direction of motion, and one of them will be horizontal, right? So in this case, we've got the vertical one here and the horizontal one here, and the vertical one's irrelevant, or the perpendicular one I should say is irrelevant. So all that matters is the horizontal, and if the horizontal component, again I should be saying parallel really, not horizontal, if the component that's parallel to the direction of motion is also in the same direction, then this is work done by the force. Okay, and so if we consider the reverse of that, let's say you've got a force, let's say even like this, but the box is moving this way for whatever reason. Let's say it was already moving at some speed in that direction. Then again, you consider the components, and We only care about the one that's parallel, which is this one, and that component is in fact working against the motion. So this is work done against, I suppose. So really, the generic term is to just say the work done, the work done by a force is the generic term, but sometimes we refer to the work done against a force, and the reason for that is to flip it from negative to positive, ultimately. Because in some sense, this work done here in the top example, this is a net positive work done, and this one here is a net negative work done. But if you then frame it as work done against, then you flip it from a negative back to a positive again. The best analogy I can think of is it's like when you talk about gains and losses. So if you talk about how much money you've gained in a week, for instance, let's just make something up. Money gained in a week. If you've gained £20, then you would call that plus 20. If you lost £20, then you would say I have gained minus 20. But alternatively, instead of saying I've gained minus 20, you could just say I've lost 20. Right? So that's the analogy here, is that work done by is like a gain, and work done against is like a loss. And all the word change means is that you're flipping the sign of the thing from a positive to a negative, or from a negative to a positive in this case. So when we say work done against a force is 20 newtons, what we really mean is that some work has been lost. It's a negative 20 net loss. Okay, so hopefully that makes the distinction clear going forward if you see that sort of phrasing. Okay, so let's finally look at a very classic example. When we're talking about kinetic energy, potential energy, you're always going to get questions about skiers, so it makes sense we try one ourselves. There's a nice picture in the textbook which I haven't managed to include, so I might just attempt to redraw it as we go, but let's take a look. You've got a skier moving downhill, passes a point A on a ski run at 6 meters per second. Downhill. After descending 50 meters vertically, the run begins to ascend. Okay, so let's just make something up like this, and let's then say this is what were we told, 50 meters. When the skier has ascended 25 meters to point B, speed is 4 meters a second. Okay, so about halfway up. We'll call that, sorry, that's my bottle rattling, 25 meters. Okay, and the speed is B. Not the speed is B, the point is B, the speed is 4 meters a second. Okay. The skier and the skis have a combined mass of 55 kilograms, m equals 55. The total distance he travels from A to B is 1400 meters. Let's note that. 1400 meters. The non-gravitational resistances to motion, in other words, friction, are constant and have a total magnitude of 12 newtons. Calculate the work done by the skier. Okay. So this is very much a question where we want to talk about energy consideration. Keep in mind that although I've kind of drawn this slope however I wanted to, the fact that there was no diagram tells us that it actually doesn't matter what the slope looks like, as long as a few things remain true. As long as the friction is always parallel to the direction of motion, which it will be, then it doesn't matter what the shape of the slope is. As long as the skier, as long as the slope doesn't sort of turn into a ramp and the skier stays on the slope itself, as long as they maintain contact, then that's also fine. And we've been told that's the case because that resistance is constant. So the shape of the slope doesn't actually matter. What matters is the change. You've gone from a height of 50 to 25. You've gone from a speed of 6 to 4, and you've gone from you've travelled a horizontal distance, which is a total of 1400 meters. Okay. In fact, actually, I've labelled this badly. I was about to say it's not the horizontal distance, because that would make a difference. Surely, that 1400 meters actually refers to the slope itself. Right, that's the 1400 meters. Yes, because otherwise the shape would make a difference. So whatever I've drawn, it's 1400 meters. So let's consider energy. So we're going to go with the way I recommend to do these kinds of things, which is to write it this way. Change of potential plus change of kinetic equals work in minus work out. And each of these is going to have a value in this case. Change in potential energy is going to be what? So we started at 50 meters, now at 25, so it's going to be a negative number. It's going to be minus the mass, 55, times g, times the loss in height, which is 25. Going from 50 to 25, it's a loss of 25 in height. And that gives us, if we take g as 9.8, minus 13,475. Change in kinetic, in this case, is, and let's do it a bit faster than usual, a half times 55, and then we can just immediately say final squared minus initial squared. Okay, and I've effectively taken a half m out within the calculation to find the difference quickly. 4 squared minus 6 squared, that's 16, minus 36 minus 20, divided by 2 is minus 10, so that's minus 550. Okay, and again it's negative, right? So potential has been lost, kinetic has been lost, we've got two negative numbers. What about the work out? Let's write it up here, make use of our space. So the work out, that is work done against the direction of motion. The total of all forces that are going against the motion, what is their work? In this case, we're talking about that resistance. So we've got a constant resistance of 12 newtons. It's going to be perfectly parallel to the direction of motion, but against it. So that work out is 12 times the distance travelled, 1400. And then you can think of this is the the work against friction. But as you can see in the form of the equation, we're going to take that away. We're going to remove the work out on the right hand side. And then finally, work in is what we actually want. That's the thing we're trying to calculate. So we can put that all together. We can say minus 13,475 minus 550 is equal to the work in minus 12 times 400, which is, oh, I didn't need a calculator, I'm just being lazy, 4,800. Oh, it is 1,400, sorry, okay. I do need a calculator. 16,800, right. And that should give us a final, let's check, of 2,775. Yeah, joules. So just to clarify what this is, what is this thing, the work in, right, this driving force? It's literally, the skier is, if you're familiar with skiing, they've got the two poles in their hands and they're pushing it against the ground and they're driving themselves forward. If they hadn't have done this, then the equation wouldn't balance out. So if you removed that driving force, then the final speed, the final potential energy lost, it might have been something different, right? So something would have had to give. So it's almost like we found exactly how much energy that this person has expended, regardless of the shape of the terrain, simply because we can balance the equation in this way, right? We know that the energy must be conserved, and we knew everything else about the situation other than their energy. What we don't know is if it was a consistent rate, right? So much like the very start slide, that may not have been a constant push. They may not have been consistently using, or they may not have been consistently doing that work throughout the whole journey. You know, if they put in lots of work at the beginning, maybe in the first 10 seconds they did about 2,775 joules of work done, and then they did nothing from then on. It doesn't matter. We just know the total. We just don't know what happened in between. So that's it. I really recommend sticking with this form of equation. It makes it a lot less likely for you to make sign errors, I think. Rather than talking about gains and losses, work done against, work done by, just think of everything as a change. Yeah. Cool, so let me give you some questions to do. Okay, so as I said, there'll be a lot more friction in these questions now. There's 4 questions, 1 slider 2, 1 slider 2, and then there's one challenge question, which might be interesting to try, which is something a little bit different. And it's less about slopes and skiing and friction on slopes and that kind of thing. So if you want a bit more variability, a good idea to try the challenge question. Yeah, so I'll let you get on with those. This is the first 2. You can pause the video when you're ready. Okay, and then a couple of exam style ones for you to try. Pause the video when you're ready. And finally, this is the challenge style question. So a little bit of physics. See if you can figure this one out. There's a few numbers in there and formulas. You don't have to necessarily understand why the numbers are what they are. You just need to be able to use the information that's been given to you. See if you can interpret it correctly. You can pause the video now.